Hey physics! So today we're talking about an experiment done by J.J. Thomson with the cathode ray tube that totally changed our idea of what the atom looked like. So just to give some perspective, this is what we thought the atom looked like for thousands of years, right? It's just a solid sphere. Each different kind of element maybe has some different properties, but they're all just solid spheres. So this is the first experiment we're going to look at that caused us to crumple up that model and start fresh. So this experiment was done with, like I said, a cathode ray tube. What this is a tube that is plugged to a power source, and inside of it is a vacuum, meaning that there's not a whole lot of gas particles in there. That would be kind of like the syringe that we had totally closed and we pried it open, but there was not very much in there. So this is a pretty low pressure system in there with just a little bit of gas. And usually gas does not like to conduct electricity very much. But when you get a low enough pressure system and when you get a high enough potential difference, meaning like a difference of charge on either side, then there is a stream. They found that there's a stream of glowing particles that come from the cathode over here to the anode. By the way, cathode just means that it's a negative charge. Anode means that it's a positive charge. So this negative charge is coming from here over to here. So J.J. Thomson, who I'm going to show you a picture of real quick here, is this guy. And he was working with a cathode ray tube, and he felt like there was something more to find out about it. Nobody knew what those cathode ray particles were at all. So what he did was he actually put some magnets on either side and found that when the magnets were strong enough, the stream of cathode rays, which it turns out are electrons, was bent. It would actually bend one way or another to be, because it was attracted to the positive part of the magnet, it was deflected from the negative part of the magnet. So we have a simulation that that kind of shows what was going on here, and I'm going to show it to you here. So this blew everyone's minds, right? Because this says that no longer do we think of the atom as this one solid sphere, right? The atom actually, now we know, is multiple parts. The charges are actually different pieces of the atom, and one of those pieces is called an electron. So here is the cathode ray tube like J.J. Thomson used. We have the cathode, which is the positive part of the, it has the positive charge on it. We have the anode, which has the negative charge on it. And it gets all charged up here. There's no air in here. And this stream of electrons comes shooting out of the cathode ray. Okay, so let's turn on our cathode ray. And you can see already that that cathode ray is bent towards the positive charge because these are electrons, and electrons have a negative charge. So we can display the particles. You can see what this looks like. We can speed it up really fast, or we can adjust the charges. So now we have the positive on the bottom. So we know it's not just going towards, like, bending up for no reason. So we can switch the charge on it. You can see that it always bends toward the positive charge and away from the negative charge. And this is true with whether we're using gold for our cathode and our anode, whether we're using silver, or whether we're using iron. Okay, so that's that simulation. So how did J.J. Thomson know that what he was looking at were electrons and not just like small atoms? So let's look at what would happen if these were atoms that were being pushed out of the cathode ray tube. So here we have a cathode ray particle, and you can see that it bends up, and this is just at like kind of like a standard, like whatever charge they would normally have, that's what that does. But let's try, so we have hydrogen, which is a very small atom. Oops. We can try it with lithium, which has an atomic mass of 7. So hydrogen has an atomic mass of 1. You don't know what this means yet, but you'll get there. Just know that, use these numbers for kind of perspective or proportion. So hydrogen has an atomic mass of 1. Lithium has an atomic mass of 7. Carbon has an atomic mass of 12. Okay, so, and we can send an atom that is negatively charged or an atom that's positively charged. So again, let's see what happens when we send a cathode ray, which is, we know now, our electrons. So it's a very, very small particle, like super duper small. It doesn't take a whole lot for it to bend. What happens if we send a negatively charged hydrogen atom? Nothing. Okay, at least visibly nothing right now. What happens if we send a negatively charged lithium atom? Same thing, okay, nothing visible. Same thing if we send a carbon atom. Why are we not seeing a change there, I wonder? Let's try it with positive atoms. So carbon looks like nothing, lithium looks like nothing, hydrogen looks like nothing. What happens if we increase the charge on the plates by 1,000 times? Let's try this. Okay, let's try our cathode ray particle first. Whoa! And like immediately, so it must be a very light particle. We are seeing that it has very, very little mass, right? Because instantly, as soon as it gets in contact with the positive charge, it's just like, zoom, it goes right to it. So let's try now with our increase of charge. Let's send a negatively charged hydrogen atom. Okay, so now we're seeing that bend. And I see that it bent pretty early, even earlier than the cathode ray before we had the super duper charge on it. Let's try a lithium atom and see what that does. Negatively charged. Okay, so that bends also. It bends less because it's a slightly bigger atom. Oops, let's try a carbon atom. So that bends a little bit. So you can see that the smaller the atom, the more that it bends when it has that super high charge. Cathode ray particles then, I mean, hydrogen is the smallest atom. Hydrogen is literally just one proton and like an electron floating around. So it's very small. But a cathode ray particle must be even smaller, like by a lot. Because let's look at this again. When we have a super duper charge on this, look how fast this goes. Shoo! It's like barely even there. Let's see it in slow motion. Now it's like painfully slow. Here it comes. Come on, cathode ray, let's go, let's go. And then even then it's like, shoo, like really fast. We don't need to see the other ones in slow motion. But that's the evidence that those cathode ray particles, which turned out to be electrons, are tiny. Like they're even smaller than a hydrogen atom by a lot. And that's what we get out of this.